Next, we're going to look at the change of variables when the domain is an ellipse. And so let's take a look at the general form of an ellipse. An ellipse is, now this would be centered on the origin. So this would be an ellipse centered at 0, 0. So the question is, how could we make this more reasonable to work with? One way would be to turn this into a circle somehow. So we have to say to ourselves, could we do? What kind of a substitution could we make to turn this into a circle? And so one thing you can kind of think of here is whatever this denominator is, if we could somehow cancel this, we can make a substitution that'll cancel this a squared. Same thing over here on a substitution that cancels the b squared. Now, whatever we're going to put in for x, it's automatically going to be squared. So you can probably see here then, if we could do a substitution that has x equal a times u, let's say, then when we put this into here, the a is going to get squared and that's going to cancel. Same with the y. Let's say if we made a substitution like this. And again, if when we put these values in for y, the b gets squared, and those will cancel. So let's substitute into up here. So we're going to have au squared divided by a squared plus bv squared divided by b squared is equal to 1. Now let's see what we get. We end up getting a squared, u squared, a squared, plus b squared, v squared, b squared, equals 1 like this. And then we get u squared plus v squared is equal to 1. So that's going to be a circle of radius 1. So this is the kind of substitution we would use for a circle centered at 0, 0. Excuse me, for an ellipse centered at 0, 0. We'd make a substitution like this. Whatever the denominator has, put that as AU. Denominator here, put it as BV. So let's take a look at this problem here. Let's say we want to evaluate this double integral, and we want to evaluate over the domain D, which is the ellipse x squared over 5 plus y squared over 64. And let's see if we can use what we just learned to evaluate this. Now, first of all, we want to get this into a form of an ellipse. So we're not quite there because we need the denominator squared. So we're going to have to make this square root of 5 squared. Make this 8 squared equal 1 like this. And now let's do the substitution we talked about a few minutes ago. We want something that'll cancel the square root of 5. And we know whatever substitutes here will get squared. So we just put whatever is under the square down here. So it's going to be square root of 5u. And same thing over here. Y equals 8v like this. So that's going to be our substitution. And let's put those in and see what we get. So we're going to get, we substitute in over for x, we'll end up getting square root of 5u squared over square root of 5 plus 8v squared over 8 squared is 1. Again, that's supposed to be a u there. It's kind of messy. But again, excuse me, the denominator here was already squared. Now, again, when we square this, these are going to cancel. So we're going to end up getting u squared plus v squared. So this is a circle, radius 1. Centered on the origin. So now we have to calculate the Jacobian. So for the Jacobian, remember we have to, well, actually, I guess we already have this in terms of x. So let's calculate our Jacobian. Then we want to take the determinant of the Jacobian. So again, we have, remember that's dx du, dx dv, dy du, dy dv, like this. And so again, take the derivative here of x with respect to u. And the derivative of x with respect to v, of course, that's going to be 0. Derivative of y with respect to u is going to be 0. Derivative of y with respect to v is going to be 8. Like this. So if we do the determinant of the Jacobian, of course, that's just going to be square root of 5 times 8 minus 0. So let me write it just a little bit nicer, like this. So now we can go ahead and set up our integral. And again, for the example, I picked a relatively simple integral. And so when we're going to plug everything in, and let me just kind of write everything side by side so we can see what's going on. And again, we're going to make it our change of variables. We're going to substitute for x and y. V. This. And then put the Jacobian. Remember our formula when we make the change of variables, we always put the Jacobian here. And that's going to be 8 square root of 5 like this. And that's going to be du dv. And again, I'm going to put a lot of steps in here. So now when we square this, this is going to be 5. We can bring that out front. And we have an 8. We're going to bring that out front. And we have another 8. We'll bring that out front. And we have a square root of 5. We'll bring that out front. And what are we going to have left in here? This will be u squared times v du dv. So just be sure I brought everything out. This was the 5, the 8. I think we got everything out front. Now, think of what we're doing, though. We're integrating over this new domain now, the circle of radius 1. So let me just kind of mark this here. Circle. So now, since it's a circle, let's change the polar coordinates. And let me multiply some of this out maybe a little bit. Maybe this would be 5 times 64 square root of 5. So again, a circle of radius 1 centered at the origin. And so that means so we're going to change the polar coordinates. And so again, remember for polar, this is going to be, let's maybe make u equal to r cos theta, and v is r sine theta. And you could do them the other way around as long as you're consistent. That would be fine. And then this is going to be r cos theta squared. And I'm going to just go ahead and put the square in right now. Square each of those. And this is going to be r sine theta. And remember, when you change the polar, you have to have that Jacobian. Remember, that's always r, and of course dr d theta. And it's a circle radius 1. Like this. And this is going to be squared, or it looks like it's going to be to the 4th. And then this is going to be, let me make this cos squared theta sine theta. Hopefully I didn't mess anything up, or d theta. Now, if you get to this point, you've done most of the work. In fact, you've done the vast majority of the work. Now it's just a matter of integrating this. And so this can be done pretty easily, just takes a few steps. So again, if you want to skip that, you can just skip to the next example, because often, I know when I do my classes, a lot of times I have them just set up the integral. And because that's the hardest part, to at least get to this point, to the point where you have to do nothing else but calculate the integral. But let me, for those who you're interested in seeing the rest, I'll go ahead and do a couple more steps. So I integrated with respect to r here. It'll be r to the 5th divided by 5. Then if we evaluate the upper bound, is going to give us 1 to the 5th, which is just 1 divided by 5. And that'll be nice. We can just cancel that 5. So that'll be one good thing that we can get out of this. And then we're going to, like I said, 1, then the lower bound is going to end up being 0. Then we have cos sine theta d theta like this. And then finally, you can probably do like a substitution. Usually call it u substitution, but since we use u already, I want to use a different letter so that we don't get confused. So we can probably do cos theta dw is going to be negative sine theta d theta, then negative w is going to be sine theta d theta. This, and we substitute. I won't, I'll leave the bounds off temporarily. So it'll be u squared. Then it's going to be a negative, so I'll put that in front. We're going to put negative dw for this. Then it's going to be negative like this. And then let me put the original bounds back in the original function. So it's going to be negative cos cubed theta divided by 3 if I didn't mess anything up. I've gone through a lot of steps here. It's possible I may have made some slight error. So if you see something different on yours, it's possible I may have made a mistake here. And so let's say, so cos of 2 pi is going to be 1. So, and then minus 0. So what are we going to get here? 64, 5. So we're going to have negative 1 cubed, right? Because, and then minus a negative 1 cubed. And just realizing what we're going to get here, we're going to end up getting, again, this is all times what's in front. So it's going to be, excuse me, that's actually going to be 0. So we, after all that work, we just get 0. But the main point of this was just to be able to set up the integral to go through the steps. And again, the key is using a substitution like this. Now, in the next problem, we'll be doing, the domain will be an ellipse, which is not centered at the origin. So we'll take a look at that next. So let's take a look at this problem. We want to evaluate this double integral where the domain D is this ellipse. And now again, notice this is not centered on the origin. Because it's this has like an x plus 5 and y minus 7. So first of all, let's rewrite this. So we get this now. I just made the denominators into squares. Now, we had a problem like this previously. If we just had an x in the numerator, we would replace x with 5u. And if we had just a y here, we would replace y with 2v. It'll really be the same thing now again, except instead of replacing x with 5u, we'll replace x plus 5 with 5u. So in other words, we'll do something like this. Let's say x plus 5 would be equal to 5u. Again, we're picking 5u because we want to cancel. And then y minus 7 is equal to 2v, like this. And now the only thing we have to do is we have to solve for x and y, because we'll have to find the Jacobian here in a minute. So x is 5u minus 5. Y is 2v plus 7, like this. So let's go ahead and make these substitutions, like this substitution right here. Let's go ahead and make that substitution into here to see what we get. So if we replace x plus 5 with 5u, that's going to be 5u squared divided by 5 squared, then plus, we'll replace y minus 7 with 2v. And that's over 2 squared. Once again, when we square these will cancel. We have u squared plus v squared equal 1 squared. So once again, our domain, our new domain, is going to be a circle of radius 1. So now we can calculate the Jacobian. We'll find the Jacobian next. And remember, it's dx du, dx dv, dy du, and dy dv. And again, when you do dx du, you get 5. Dx dv is 0. There's no v in the x equation. Then dy du is 0, and dy dv is 2. And then if we do the determinant of this Jacobian, we're going to get 5 times 2 minus 0. So the determinant of Jacobian is going to be 10. And so now we are ready to substitute into our equation. So our equation was 3x plus 5y dx dy. And we're going to substitute in for x, which was 5u minus 5. And then over here for y, we're going to have y was 2v plus 7. And then the Jacobian was 10. That should be du dv. We're integrating over a circle of radius 1. And let's simplify this. We're going to pull the 10 out front. And then here, this is going to be 15u minus 15. And this is going to be over here at 10v plus 35. Du dv. And this is going to be 10, and we can simplify this a little bit. But mainly we're just looking to try to set these up properly. Now, again, remember we're integrating over a circle of radius 1. So we need to we need to do this in polar coordinates. So we have to switch to polar. And again, we're going from 0 to 1. And then theta is 0 to 2 pi. And we're going to, again, we're changing the polar. That's going to be r cos theta. Again, let's say we call u r cos theta and v r sine theta. So we're putting in here plus 10 r sine theta plus 20. Again, remember when you switch to polar, put that Jacobian in, which remember that's always r d theta. And once again, if you can get to this point, you've done almost all the work. So if you had to just do a setup only, it will be getting to this point here. And now the rest of it is just doing this integration. In fact, I will probably skip that here.